Thank you, everyone. I'm glad to present you this session today on bridging domains, transfer learning in AI-powered text recognition. From museum labels to ancient text, I'm going to present you two projects I've worked on and how we used some knowledge we acquired in one domain and use it in a completely different domain, but using a similar framework when it comes to AI. We're going to have some hands-on activities, some demos, as well as a bit of theory, bridging domains between museum labels and ancient manuscripts. So in our case, one papyrus and museum labels that we have here, DMSN, and in other collections that I will present later. So the key themes will be AI automation and expert validation and how that increase our speed, help us with accuracy, through the expert validation, and can give them some cultural insight at the end. Then we have the scale of efficiency themes with the preservation. What could be the big idea to digitize massive collections responsibly? And of course, one of the latest theme is transfer learning across domains. So apply modern solutions to ancient texts, which is the core theme of this presentation. What to expect? So no coding experience required. I have two hands-on activities. That should be pretty straightforward, but I will present them to you later. The idea will be really to focus on ideas, your experience, what you expect, not the syntax of the actual process. Then we're going to have two live demos on two different projects. I based this whole session on two case studies that I worked on. The first one is called Etymological Label Information Extraction. It's a project that was born here at the MSN roughly 2 years ago. And the idea was, how can we process a large number of pictures of insect labels? Here at the MSN, we had a big digitalization project that started in 2021, I think, 2021, 2022, and that lasted 2 years with a partner called Papyri, which is from the Netherlands. And they took 600,000 pictures of insect specimens in our collection. So it was a mass digitization project. We had at the end a vast amount of digital material, of images. And the question came is, what do we do? With all this, what can we salvage from it? Do we just have the pictures, or do we try to get more from it? We started experimenting with AI tools out there. Here I have an example of an image. This is actually from Antwerp, which is online repository of specimens and their labels. We first started to experience with online repositories, and then we moved on with our own data. How it works. So in the case where you have a picture with multiple labels like this one, the goal was to first find the label inside the picture. That requires a certain type of AI that I will talk about later. And then the second step would be to classify the labels. We found out when it comes to OCR, HCR, so handwritten text recognition, optical character recognition, OCR being better with printed material, as you can see here, and HDR being, of course, better with handwritten material. We found out it's better to separate this label in advance. In our case, in Berlin, we have a lot of barcodes and identifiers inside our pictures linked to the specimens. And for our analysis, we also wanted to filter out these ones. They don't have to be, but when it comes to computation power and cost, sometimes, because OCR, depending if you use an open source or closed source, it can cost you money. My advice is, if you decide to go that route, to try to filter as much as possible before using OCR on your data to make sure, one, it goes faster and it costs you less money. Based on the label type, we use either OCR or HDR or manual transcription in some cases. And then at the end, the goal would be to have a JSON file. A JSON file is a type of file where you have structured data in it. Let's say you're going to have a value ID And then the ID would be the inventory number or whatever identifier you use. You will have location, you can have taxonomy, you can have the collector, and that JSON file contains all these data, or the file name of the picture, that type of thing. That was quickly the framework we were going with to treat this large amount of picture. And why it matters, beyond having a lot of pictures and trying to know what to do with them, there are also a lot of specimens worldwide that need digitizing. And as I'm sure you all know, in natural sciences, cultural heritage as a large, we don't have a lot of people to digitize the specimens and to extract the meaningful information they contain on their labels, or even the specimens themselves. The second test study, that's a bit more specific, but the challenges are very similar when it comes to digitize it. I worked on a second project with FU in Berlin. And when it comes to archaeology, especially near ancient studies like Egyptology, they are not advanced really in the whole AI approach. It's a way more old school type of approach. It's still very much manual focused for multiple reasons. But so there is also a lot to experiment there. Here, the goal would be, how can you identify single signs within a papyrus? Simple. Maybe you can classify it, maybe not. But here, for example, it is a type of handwriting recognition. Sure, it's signs, it's not our language, but we have ligatures, we have signs overlapping each other, we have a lack maybe of white space, we have different colors, sometimes different handwriting. Not here, but it can happen. You have damaged text, you have different colors in the background, like used material, things that you can see also in some collection when it comes to handwritten text. This one has a language called hieratic. Hieratic is essentially hieroglyph dialect that is like a more handwritten, more abstract version of what, like on temple walls or things like that, of the normal hieroglyph. It's quite challenging to digitize. And the process was a bit different, of course, because we don't have the same data, but it was quite like we use the same framework. Instead of finding individual labels inside a picture, we try to do the same, but how do I identify individual sign in the picture? For that, the system we use is called a segmentation model, an RCNN to be exact. It's like you find a lot of documentation online. When it comes to segmentation, you can apply to segmentation to anything. When I heard about morphology, literature, like how to find certain elements in literature or how to identify like parts of a specimen, segmentation is something that is used a lot. Like a program like Tektron 2, for example, would be that style of segmentation program. Segmentation can be applied to all type of material. And this is what we did here with the Tektron 2. But nowadays you have a lot of documentation available online and a lot of notebooks and a lot of explanation. And with a bit of time, I think it is possible also to understand this system. In the previous slide, on the second step, we try to identify whether a label is handwritten, if it is printed, if it is an identifier. We classify what we segment. Here, we also classify it by using standards related to Egyptology called the Gardiner Code. The Gardiner Code identify what a sign is. Is it a seated man? Is it a seated woman? Is it a god? Is it a bird? Something like that. And it has specific code to it. I won't get into details here, but same principle. We classify it with, that's not a segmentation model, it's called a classifier. You have a lot of classifiers out there. Essentially, if you want to identify an object in an image saying, oh, that's a dog, that's a cat, that's a chair, that's a classifier. It's also the type of technology where you have a lot of documentation about them, but we can talk about them later. Then for the third step, we use expert validation. We actually also use expert validation for the first case studies, but it's a bit more steps. We will have a look at it in the demo. But I'm a big advocate for expert validation, essentially not to have the AI, not to take the results of the AI for the truth or like 100% I trust it. You still want to have some type of validation first to help the AI become better, but also when it comes to cultural heritage, natural sciences, there is a lot of context. And the AI is as good as what you give it at the end. And I think a person will still be more aware of the context than an AI. And it really helps to have some type of tool where you validate the results. You said, oh, this is good, this is bad, this could be better, that type of thing. And that's what we applied here. And ultimately, what we extract, what we validate, if it's good, it can be used to improve the AI. And it can then also be used to integrate into academic databases long term. Same with the first project. Whatever data you extract from the label, it can be applied, like it can be transferred to your own databases within your institutions or to online repositories. And what it matters when it comes to Egyptology, or it can be Assyriology, whatever ancient discipline, archaeology, where you have very limited number of experts. It's the same problematic. They don't have a lot of people. You have very limited expertise, and you have a lot of material that is not digitized. Again, same problem. The scale of the challenge, why automation matters. When it comes to Eli, we have, so hard to estimate, but billions of specimens in natural history museum worldwide, most of them not being digitized. Of course, that depends a lot on the size of the institutions, on the budget, on the personnel. Also, another value that is a bit difficult to estimate, but based on what I've seen here in Berlin, you can have between 5-10 labels per specimen. And that can get, if you start to add up all the labels you can have per specimen and what you have to digitize, you can get really crazy numbers. Here, I'm mostly talking, as I did not specify here, but I'm mostly talking about insect specimens. I'm not even talking about paleontology or mineralogy, which the numbers are astronomical. And we did also, on the third point, some tests. We wanted to see how fast, on average, when it comes to etymological labels, how fast do we transcribe them manually? Depending on the difficulty, depending on the experience of the person, on average, when it comes to printed, it can be 4.8 minutes and handwritten 5.8 minutes. It's quite of a lot. After we had, it was with some labels that were quite difficult. Let's say that had a lot of information. And in our manual transcription, we also have steps where we try to classify the type of content the label has, and that there is like maybe a minute of classification quickly before manual transcription, but it's still a lot of time. And if we add up to how many labels we have and how many specimens, it's going to take, I don't know, hundreds and hundreds of years with people working full-time. Total efforts, like 50,000 people for that amount of years. It isn't manually, it's impossible. And according to sources for etymological labels, still when it comes to specimen data, 85% of actual data about the specimen are still trapped at not images, but the labels of the specimen. If every museum employed full-time transcribers, it would take centuries to finish. That's when automation comes handy. For the second case study, erratic AI, same problematic. We have 100,000+ papyri in collection worldwide, still awaiting detailed analysis, even a picture, or some don't even have pictures of them. When it came to the papyrus I showed you before, to manually annotate that papyrus, to prepare the data set for our project, it was 605 signs manually annotated for 20 lines. And that probably took, I would say, 3 days, 2-3 days to complete with documentation. It takes quite some time. Again, you have a few people working on it and thousands of papyri that still remain unread. When it comes to Egyptology, human expertise is essential, but still painfully slow. How do we help that? Now I'm going to have a quick introduction of transfer learning. I found this example of what transfer learning is. Let's say you have a child and you teach a child how to read. You're going to first start, let's say, at least that's how it was for me. You have a book, you have the alphabet, it's a nice printed letter alphabet in a handbook, and that's how you learn the letters, that's how you learn to read this nice text. And then later on, you're going to try to read something that your teacher wrote by hand, or that your parents wrote, or that a friend wrote. You learned on this nice script, but then you applied this knowledge on a more difficult type of reading later on. That's pretty much what transfer learning is. You learn the base on something quite simple, straightforward, that is easy to learn, and then you make it more difficult. You apply it to more specific task. Essentially, the goal would be to each step you add, new things you learn, you don't want to start over again. Because imagine if you have to relearn everything from the beginning, the time we would lose would be insane. Well, it's the same for AI. When you train a model, let's say, to read a label, if I train a model to recognize a text in an image, and for that, I'm going to need thousands, if not tens of thousands of text, of images of text, of labels. And let's say I'm training it on 100,000 images of printed labels. I want to use the knowledge that AI learned and apply it later on. That would be my base model. I don't want to have to retrain it completely on a new set of 100,000 handwritten labels. So first, you try to train and teach the AI what you want to do on an easier, still large task, and then adapt it to something a bit more challenging. And when it learns on this large first set, it's still going to learn, let's say, what a text can look like, where the edges of a letter, maybe certain shapes, how to ignore the background. It's still going to learn the basic of script. Then, if you want to apply it to something more difficult, like handwritten historical documents, you're going to keep the general skills, which is where the text is, the different shapes, ignoring the background, and try to fine-tune the model. So that would be like the term use. You fine-tune the model on your own little data set. So when it came to Ellie, for example, we use a base model. We use a base model called ImageNet. ImageNet is a type of model that was trained, I think, on 14 million images. This data set of 14 million was essentially the model learning how to recognize an object in an image. That's why it learned to recognize objects in images. When you add on your new data set, you just fine-tune it to learn very specific things. Okay, now you know what to look for. You don't want to look for a text. That's a type of text I want you to look for. The idea would be at the end, because we are all limited on our computation power. Like if you just have your laptop, for example, and you don't have a huge cluster, it will be impossible if you don't use an external, I don't know, GPU or something, to train something with hundreds of thousands of labels. Like you need something that has a base already, that knows the basics. And then maybe with a few thousand labels, maybe a few hundred sometimes, you can teach it to learn your very specific text. I'm not saying it's going to be incredible and you can then scale it up, but it's a start. It's really a start. And that's how it works. And that's how we are doing it here. First, because we don't have that amount of data available right now to train it, and also the computation power. So we have to adapt. I made this little chart to show you what I just explained to you. We have the source task here. We first going to have a base model that was trained on the, let's say, modern printed documents, quite an easy task. It's going to learn general skills, where the text is, find the ages and shapes, ignore the background. That's what it knows. Then we're going to retain these skills. And that's when we arrive and we have our own data sets, let's say of handwritten documents, and we try to fine-tune it to our data, specific handwriting styles, the special features when it comes to Old German, for example, Sütterling, which is a type of German alphabet. So let's say make it like training specifically to recognize that alphabet. And at the end, the goal would be to have high accuracy on this type of documents using minimal new data. Since we have a large base with millions, I was trained on millions and millions. Those, by the way, are available. It's not like we have to do it ourselves. They're already available. And there are models that you can find that are often automatically linked to segmentation models or classifiers. It's not something we have to do ourselves. It's already there. But that's the data we have to provide, though. We have to make our own data set. The data set has to be very specific on what we want to do. If I want to, let's say, teach my model to recognize handwritten label from Brazil from a Diptera collection, for example, that data set needs to reflect that. Like, it's very important because the AI will learn only what you give to it. It's going to have all the biases, all the goods too that you give to it. Now, I'm going to talk to you about the Ellie project in a bit more details, and you're going to recognize certain things that I talked about. We first started with the basic text of how to recognize a label in a picture. That was our first goal. We had this project called Bees and Bytes. That was a very old digitization project, and we had a few thousand pictures of that project just sitting around, and the collection curator at the time wanted to know what the labels contain. We had all these pictures, but we didn't have people really to transcribe them. We tried to find a way to make that task a bit easier. And the first thing was to extract this label from their main picture. This is where we use a segmentation model. And that segmentation model, you can see here in red, the little bounding boxes, could find these labels, and then we could crop them out, creating a multi-label image to a single label image. That was our goal. Then our next goal was to filter a lot of empty labels. I don't know how it is in your collection, but when we digitize here, at least we used to in Berlin, we would take pictures of the recto and verso of the labels, and the verso often, most of the time, didn't have anything. When it comes to computation, it's not really efficient to digitize an empty label. Of course, it's interesting not to completely delete it, but to retain it somewhere, but there's nothing to extract, nothing to look at. It's pixel-based, so it's not really text-based if it is with other labels or on its own. But if it's on its own, like to filter empty labels, we didn't use a classifier. We used a rule-based script, which means we wrote a script so it would recognize how much dark pixel there are in the image. Because our empty labels don't have dark pixels at all, because usually the text is written in a darker script than the labels. So that's how we filter them. We don't use a classifier. But when, like for classifiers, for example, for identifiers, so here we have a QR code, but identifiers can be any symbol, depends on your institution, right? Like we use a classifier to filter them out, like to filter them from the rest. We still save them in our pipeline. They're not deleted or anything, but we just put them in their own little folder because we don't want to compute them. That would be a solution, I would say, like classification, AI classification, more than segmentation. Segmentation is really to extract an object or to identify an object. Speaking of classification, so once we detected the image, the label in the image, filter the empty labels if we have some, sometimes we don't. Then we apply classifiers. We have two big ones at the moment. We have one that identifies either if the label is printed or handwritten. In this case, also, I want to point out, so it's a bit difficult to see, but here, sometimes you have mixed labels with handwriting and with printed text. In our case, we trained our model to recognize the script that is the most present on the labels. Usually, when it comes to mix, usually handwritten, like handwriting, is the most present one, but that's how it will be filtered, essentially. We could have had a mixed category, but that would have added an extra step, so we wanted to be a bit more efficient. And then for our case, we also apply a QR code or identifier classifier. It also separates this type of label from the rest. And that's just for pure computation, like later power. We don't use the OCR or HDR on them. Then for the rest here, what we do is we have OCR extraction. For OCR, we experimented on two at the moment. We created a whole module with Tesseract, if you know of it. It's an open source OCR program. Since it's open source, it requires a lot of image preprocessing, and image preprocessing, that would be like, how do you prepare the image the best way possible so the OCR can read it. Usually OCR, they like high contrast. For pre-processing, you're gonna have all your dark pixel, make them darker, and the background make it whiter. You have a high contrast. You're gonna remove what we call the noise. That would be dust, shadow, things like that. How to make your image as clean as possible. And Tesseract requires a lot of that. It is quite a lot of work. But we wanted to test something that we knew was really performant. And for that, we tested Google Vision API. Google Vision is a Google product that it's an OCR where you can connect to it directly through an API. You have your script and you can send Google Vision the images you want to transcribe, and it sends you back the results in whatever format you ask for. It is very good. I think it has a high accuracy of 98, 99% transcription on our printed labels. We are currently testing it for handwritten labels too. Tesseract is not as performant, it's closer to 75%. So there is still a lot of work to do here, but when it comes to OCR, unfortunately, closed source like Google Vision or Amazon Recognition are pretty much unbeatable. It's the truth. Like, I think I know in the NHM, Natural History Museum in London, and we were there a few weeks ago, I also experimented with Google Vision. Google Vision, yeah, it's one of the best OCR in the world, and they can process a large amount of data. Since we're in Germany, when it comes to data laws, data protection, that's something also that has to be very careful, especially if you want to apply it to like museum-wide or institution-wide, depending on where you are. We just did some tests. Yeah, so it really depends on your copyrights and things like that. That's something to also check before doing tests like that. Google Vision is quite cheap. I think we transcribed close to 26,000 pictures for 20 euros. Of course, that's why we have all these steps before. So we filter as many images as possible, so it's cheaper at the end. And I think it's 1 cent a picture, an image or something. It's still quite cheap for the result. And for Tesseract, we are very much open source advocates. So we want to also still work on it and still find a way to be also less dependent from the big fish like Google and Amazon. When it comes to handwritten labels, that's something we are currently developing. At the moment, I have manual transcription here, but we also have done tests with Keras, which is also an open source program that requires a lot of image preprocessing, We are currently testing it. We're also doing tests with Google Vision to see how it handles handwritten labels. Finally, we also are testing with Transkribus. I don't know if some of Transkribus, it's a read co-op project. It is, I would say, between closed and open source. Transkribus can be quite expensive. It's also a service, and they specialize in handwritten historical documents. It's a type of platform. It's very user-friendly, and you can there build your own HDR model. I think it's quite decent. It just can be very costly, but they give you free credits at the beginning. I would say this is a good start to experiment with handwriting, like with HDR. You can segment your text, so you can really teach it where the text is, what you want to read. You can upload your own data set with your own pictures, your own script. I would say this is a very good way to experiment with HDR without getting too complicated. They have a platform online. You can also download it as an app, I think, on your laptop. The only problem with Transkribus, two problems with Transkribus, is their API doesn't work. At least they didn't last. Maybe it's different now. You have to use their app. You have to use their website. You cannot just have your own environment and send it to them. You have to use their thing. And the second thing is it's quite expensive. Google Vision is cheaper. That's why we are experimenting more with Google, but I would still recommend Transkribus. Once we have transcription outputs of our labels, whether it's OCR or handwritten, we send them to what we call a clustering module. Clustering is essentially, there are many types of algorithms when it comes to clustering. Clustering is what we call an unsupervised method. Unsupervised meaning we don't tell the algorithm, the code, what to look for. It looks for things on its own. Here, what you had at the beginning, all of this that's supervised, we tell the model, we tell the AI what to look for. I'm looking for handwritten labels. I'm looking for printed. Here, clustering, what it does is actually transcriptions is going to look for similar patterns, for a similar type of content, not duplicates, not exactly the same text, but it's going to look at the different patterns and try to group them together in clusters. You can adjust the cluster threshold if you want your clustering to be very specific. You can adjust that, or if you want it to really, I don't know, be very large, not too specific, then you can also adjust this. The more specific you are, the more clusters you're going to have. And the less specific, the bigger the clusters and the less clusters you have. We experimented that on the highest threshold possible and the lowest threshold possible. And it's very interesting because when you look at lower threshold, clustering can actually group our labels based on whether it's a label that talks about location, if it talks about taxonomy, if maybe it's a type of identification, if it's about a collector. And if you will cluster it at a higher threshold, then it's going to cluster, oh, this is all the location that we could find about Vietnam. All these insects were found in Vietnam, or all these insects were collected by the same collector, or all these insects were collected in this date range, etc. Depending on the filter, you can really have very specific results. And I find that very interesting for multiple reasons. First, it's unsupervised, so I don't need to train it. I won't have to train it on new data. I won't have to maintain it long term. It just always works the same. It's really reliable. So it's a very easy tool to use. And the second, when it comes to digitizing data, when at the end you want to enter this data in a database, you want to make them available somehow. And ideally, you want to know where is the location, what is the location, the date of your specimen, if it was collected, the taxonomy. And this type of clustering, especially like we use it when we have thousands and thousands of labels, something that on my own, I could not begin to filter. It would take me a very long time to filter this data, to classify them and to enter them in a database later. And the clustering kind of does this work for you in advance. So it's a tool very useful for very large data sets where you want to distinguish patterns in them. And from a research point of view, this is not quite my expertise, but from the researcher I'm working on for this, for him, it's interesting because he's going to see certain patterns in the data of one label, let's say, that was found in a cluster with other labels, but it wasn't like collected at the same time, and they find some similar pattern in the taxonomy, things like that. They can show patterns that you might not have found yourself because of the amount of data. And so, yes, I think it's a very interesting tool. I would really recommend clustering when you have very large amount of transcription data. It can really gives you very interesting results and pre-digitize, let's say, this data for you. And when it comes to clustering, we also have a validation system. So we validate whether a cluster is correct or not. It's a bit complex, but the goal will be to create a database based on this clustering. If we validate a cluster, we're going to retain a label, let's say, representing that cluster and keep it later for future reference to compare it to future data we might cluster as well in the future to slowly accumulate data that share similar patterns. We're currently in the process of publishing in Methods of Ecology and Evolution journal in the UK. Also, there will be more data about this. And very important, also for the other case study, every time we test a module, we also have its evaluation. It's always important to, when you train a module, to have also a validation data set that tests how well your module did. That's something we did for this pipeline. Now I'm gonna show you two interfaces. The first one will be on the first part before the clustering, and the second one will be the validation of the clustering. This is an application we built ourselves. We are not professional GUI developers interface, but we experiment with things. And there is this program called Streamlit that allows you to build like interface in the most basic way possible. But so that's what we did. And I thought it was a good idea just for demonstration. I don't know if you know what Docker is. I'm not going to go into a lot of details here, but essentially Docker is a way to ensure that your software, your program can run on other people's computers. They don't have to completely adapt to, because everyone has a specific way of doing things. And Dockerizing things makes things easier when you want to run a program on different environments, different machines. Yeah. I'm going to walk you through this. Here, we can select the pipeline type. We have different types of inputs when it comes to our project. Not just here in Berlin, but also worldwide. You can have images containing multiple labels, or you can have images with just one label. It really depends on the collection. It depends how you're decided to digitize your project. I've seen these two methods applied in different ways in different collections. It really depends on the person needing it. For that, we have to build two different paths from the beginning. When you have a multi-label image, you're going to have the segmentation coming into play to find the label within the image and crop it out. And when you have single labeled image, you're going to skip that part because you don't need to segment it since you already have a single label. Here, input directory, where my data are, my inputs, and here my outputs. Those are two multi-label image, for example. Here it is from a project we had in Berlin. Here you can see one label that contains a locality, collecting event. And here you have what we called a NURI here in Berlin. It's an identifier, QR code identifier, typical to Berlin. But you can also have QR code identifiers in multiple collections. I've seen them, for example, at the Smithsonian's, barcode, you name it. And this image here is from the Papyri project, digitization project we had 2 years ago. And so as you can see here, the labels can be positioned in all kinds of ways. I showed you clean ones, very aligned right now, but they can also be like this. You can have the labels upside down sometimes. I don't know why, but sometimes they're upside down. They can be on the side. Very diverse data set, as you can see. Here you have the file number, file name, and the preview of all the data we have in this directory. For this test, I just put 2. We built this test so we run the whole pipeline in one click, we call it. But the pipeline is also modular, which means I could also run one module at a time if I wanted. If I just want to run the segmentation, I just run the segmentation. Or if I want to skip one module, I can skip one module. The advantage of having a modular pipeline is that you can pick whatever you want, do your own menu, and adapt to it if you want to. I also wanted to know the analytics. Okay, we had what you could see before. The analytics of it was to see how much your computer worked, because we all have different computers. Mine is a MacBook Pro, for example, with an M1 chip, and it can run the full pipeline. But I know if you have, at least at the museum, the Dell computers, laptops we have cannot run certain modules because they don't have the graphic card for it. Either you have a cluster, so a big computer that you can connect to and it runs it for you, or you're going to have to find a laptop that can. So that's also a disadvantage here. It's still a very important parameter to take into account if you decide to look at AI developments, is the infrastructures you have. Before I looked into the full results files, I'm going to show you the different images it generated. You have different set of output. You have first, you see it in the file name is for every step, we add something to the file name. Label means that's the first step, the segmentation. It found this object that's labeled 2 in the image, and it found also this object and it's labeled 1 of this image. We keep the same file name and we just add this little thing here at the end saying, okay, that's label 1 of this big image, and that's label 2 of this big image. Then we move on. And here, after that, we know it's not an identifier. It's not. And it's also a handwritten label. I would say every time you have a step, whether it's a pipeline like this or you modify your data, it needs to be documented in some way. It sounds maybe a bit basic when I say this, but often we don't document every step or we forget something, and it is a nightmare to try to find what a file was originally or all the steps you have done, especially in complex pipelines or projects. Everything has to be documented, even if we don't need it at the end. Same here. It's not an identifier and it is handwritten. These 2 handwritten labels will, for the moment, not be used further right now because whatever was identified as printed here, for example, it's not an identifier and it's a printed label, this one will be sent to Tesseract for this, because for this demonstration, I'm only using Tesseract at the moment, and Tesseract is horrible with handwritten label. I would not recommend. And also, before I forget, this label here, it knows it's an identifier. Here it's written, so it will not be sent to Tesseract also. It could, but why bother? And here we also save the image preprocessing step that's created right before we send it to Tesseract. What I was talking earlier, to make the image as readable as possible for the OCR, that's what it looks like. High contrast, remove the noise, so try to make it a bit cleaner edges. Sometimes we have something called deskewing. Deskewing would mean sometimes it tries to align the text horizontally as much as possible. The lines are perfectly straight, so it makes it easier for the OCR to read. We didn't have that here, but that can be also a step. And that's what's sent ultimately to the OCR. And something to take into account for etymology collections, you also have holes in labels for those who know where the pin was. And this will be read by the OCR as some artifacts, a big black dot or something like that, even with Google Vision. Anything that is present on your image can have meaning for an OCR. That's also something to know. And these are all the outputs we produce. Not all of them are useful, but it's a way to document every step. So we use CSVs. If I start from the very beginning here, for example, it should be empty because we have no empty labels. It's not really interesting. Here you have the non-empty labels. Here you have, it doesn't really matter, like just the order, the file name, the class, what it was classified at, and the score. That's how confident the model is in its prediction. That's the type of metrics you see quite often when it comes to AI. It can be between 0 and 1, 0, 100. The higher it is, the better, and the lower, the worst. It's also for you to have an idea of how good your model was, like how confident it is, and if it needs maybe a bit more training on some classes. This is the segmentation prediction when it identifies a label in the picture. And here you have the coordinates of where the labels were in the picture. I won't get here into too much details, but all these data sets, when you produce them later, can also be reused to train more models. Because a model will train itself to recognize this object on these coordinates. This can be input for later model training. And all the data we produce in this project, we also make them available on WiNoDa GitHub. People can use them if they want to train their own models. Those are not non-identifier images. Again, same idea, file name, the class, the confidence score of the model. Then we have, for these two especially, what we called natural language processing work. That would be computer linguistic. That is studying and analyzing the language. And we do a bit of what we call post-processing. We try to clean all the weirdness Tesseract could produce in our data before sending it to clustering. Because the cleaner, the better the transcript is, the better the clustering. It doesn't do much, but for Tesseract produces a lot of what we called artifacts. I don't know if I have an example here, not really, but sometimes it's going to produce, I don't know, a random A in the middle of the sentence with like multiple white spaces around. That could be like a piece of dust, Tesseract interpreted as an A. Things like that. We try to make it a bit cleaner using NLP, and hopefully it helps a bit. But I would not recommend though modifying too much, cleaning too much, because you could also delete important data. Have to be very careful when you do post-processing. The corrected transcript, this is what's going to be sent to the clustering later. And this is what it looks like. This is the type of JSON file we get from the OCR, whether it's Tesseract, whether it's Google Vision. That's the structure. So you have the ID, that's the file name, and the text, the output that OCR transcribes. So actually, it works pretty well on these particular labels because they are very easy to read. So this is what we're going to send to the clustering. And here we have also an extra JSON files where we have added the confidence score of the OCR, how confident it is in its transcription. And that is useful data for us. Then we created this. We tried to have one big file where we have all the steps recorded. I think it's important for data management later on to also have a text, one big JSON file that records everything. We start with the file name and was it empty? Is it an identifier? Is it handwritten? Is it printed? It's true. Was it rotated? Because we also have, I did not mention it, but we also have a rotation script that rotates the label, turns them back to 0 degree if it was like, if it's 90 degrees, or if it was twisted, the OCR can read it properly. But that's something we have a lot in our collections. I don't know if it's the same for everybody, but an OCR will always perform way better if the text is straight, horizontal at 0 degrees. You have the OCR output in the confidence, and finally the post-processing with the NLP here. Yeah, and the more modules we want to add, the more steps, the bigger that file will become at the end. Now I want to show you the other one. I won't spend as much time explaining everything, but I want to show you the rotation. Here we have single label images completely alone, because in our case, which was a bit strange, is Papyri provided most of its output as single label images. The image from Papyri I showed you before that was multiple labeled in one image, that was actually a mistake from Papyri. Most of their labels were already cropped from the original image. That's how we got most of the output from that project. We had to find a way to deal with them. We applied the same pipeline, except we skipped the segmentation part. It's the same process. I must have to start yet again. And here, and we start again. Here you have all the steps that are currently being performed. You can see your pipeline working one module at a time. And here, that's your computer, how it's doing. You want to see it still working, going up, not too much, not too overloaded, but that's to see how your computer is doing. And we have the same type of output minus the segmentation. Here you have all of it. Oh, sorry, this one, for some reason, didn't work. But what I'm interested in is the consolidated results. Yes, this is what I wanted to see. If you don't rotate properly, this is what happens. With Tesseract, with Google Vision, actually, we found out that sometimes, not all the time, we don't know why, Google Vision can rotate the labels sometimes. But yeah, rotation is a big issue for us, and we are working on it at the moment. This is the little demo of our pipeline I wanted to show you. And we try to make it as user-friendly as possible, because if I have to give you, the goal would be to use the terminal of your computer as little as possible, especially if you're not familiar with it. It can be very bothersome really quickly. Once our labels are clustered, we do what we call validation. I won't show you what the clustering file looks like, but essentially it's a big CSV when you have cluster IDs. So cluster ID would be cluster 1, cluster 2, cluster 3. And in each cluster, you have all the file names and their transcriptions of the file names of the labels and the transcription that are present in this cluster. And if we are right, those labels should have similar pattern, similar type of content. But to make sure, we created this validation interface. We have 435 clusters for a total of that amount of labels. We validate them one at a time. And what we did is we measured using Levenshtein distance. Levenshtein distance essentially measures how similar the contents are between labels in your clusters. It gives you a score at the end of how similar it is. The higher the score, the worse. The lower, the better. For each cluster, we took the 2 furthest label in score and have them here in the interface. 2 furthest label per cluster here, and we validate whether that cluster is good or not. Even if let's say they are quite distant from each other, the distance could be created by an extra white space. Maybe the OCR made a mistake on a letter and changed it. Maybe there was an extra dot. All these things add up and create a larger distance. But it doesn't mean the content is not the same. What we do is we have the images and we have their transcription, like here, and we compare the transcription. Here, for example, the model did not. That's why, for example, here there's a distance because the T wasn't transcribed. But the content for these 2 labels is actually similar. What I do is, if that's similar, I'm like, okay, save decision. This is correct. I can say it's different, and then it saves it. And then I'm going to move on to the second cluster. Again, I'm going to look at the two labels and then transcription and see if it's correct or not. For example, here, this date, like it's the same location, but here the elevation where it was found is different from the other one. That's why these labels do not belong to the previous clusters. And I repeat the process again and again. And at the end, I have this CSV that kind of curate what I did, whether sample A of label A, sample of label B, so file name and transcriptions were similar or not, same content or not. And here that's the Levenstein distance, for example. That's for on analytics, if you have any notes, and when it was done. So this wasn't validated yet, so that's why it's empty here. And you repeat this. And the goal would be to keep this type of curation. There are images for later reference when we want to cluster more data later. Let's say I want to validate more clusters. I can compare if I've seen this label before, have I seen similar contents before and previously. That's also one way to digitize data, to like avoid repeating if I want to not digitize the same type of content multiple times. Also for space purposes, computation. But I can correct it if I want. But so far we haven't discussed about it. That's something I would have to discuss with collection management. But I would like to have automatic correction. But this is also a very delicate subject because I could also, depending on my expertise, remove things. But the goal will be to correct when you validate at the same time. At the end, you have a very clean data set that you can reuse later when you cluster and digitize more data. This is the validation interface. This is just for the interface, but this is one way for you to create curation content. I'm not saying you should do exactly the same thing, but clustering is a very useful tool when you want to classify large amount of data. Here we have 10,750 data. For me to classify what is what will take forever. And this is a very high threshold of clustering. So it will be very precise when it clusters. Even if it's the same location, if the date is different, it's not going to be clustered together. But here I could have done it with a way lower and I would have all the location clustered together. I will have all the taxonomy. That could be helpful. And if I do this validation system, like I could have already pre-classified data. I don't know if name entity recognition, so that would be to say that this text is a location. This text is a taxonomy. And that could be a way to prepare your data set for that type of analytics with AI later to integrate to databases. We're going to have our first activity, which is an approach, so different AI approaches and their biases. And there will be a link that will be posted. I would recommend you open it either with Google Chrome or Firefox. It is an HTML file, so it should run on everyone's computers. And it should last between 15, 20 minutes max. You have different sections. And this is all mock data examples, more or less from real life experiences. The first one will be to analyze OCR methods and their accuracies. There would be the traditional OCR that, for example, you already have a nice isolated formatted text and you send it directly to the OCR. You have also the methods where you have the two-stage pipeline, where you have the image preprocessing and the OCR right after. And then you have the end-to-end pipeline that would be to just do everything in one step. Instead of having two steps, to do everything in one big step. And here you have some questions based on what you see. You have a plot and what the plot means. And here you can navigate between each technique and you're going to have different numbers, different meanings. And you have questions about these three different here. And the question, like the answers are all in here. Then you have a second question that would be the image quality. In fact, that's something I haven't really mentioned, but the worse is your image quality, the worse the AI processing will be, especially if you treat image directly and not just text, transcribed text. Here you have 3 questions, and it will be based on this little table here. 3 questions. Each question is quite straightforward. I wouldn't write too much as an answer, just based on the graph and also your own opinions, your own feelings about it. You just give a really quick answer. Then you have a third section that would be on biases. What can affect AI in cultural heritage, for example? Here you're going to have a few examples: handwritten versus printed, multi-language, historical spelling variation, label conditions. Here you have again 3 questions, and you have a fourth section that's based on your research and your problematics. I gave potential examples of applications of AI, different domain, but that would be how these approaches work for your research, what you would need to adapt, what type of work would you need to do in advance to adapt to your specific material, and how would you handle quality control and validation, and what type of AI would you choose, what is more important to you, speed or accuracy. So AI excelled at really process large amount of data and give you analytics. And you will really excel at giving context, like in the decision of the AI, and put it in a better frame of your research. And that's something AI cannot really do, because it will only be good at what you give to it. And together, you can have this nice combo of speed, accuracy, and then add cultural knowledge at the end. The critical question when it comes to the FAIR principle: how do we make sure today's digital work is still usable in 50 years? Honestly, I don't think anyone has really an answer to that right now. Where are we going to put all this amount of data is still an issue right now. But what type of format are we going to use? What type of standards? We have FAIR principles, but how do they hold on with how fast AI develops? Then we have all the bias and representation. The AI is only able to recognize whatever you trained it on. If you train it on only certain types of data, it's only going to be able to recognize certain types of data, these types of data. For example, we have more development in printed labels. AI is better with printed labels, like Google Vision or Amazon recognition, but we did not put as much effort when it comes to handwritten labels, because it's more difficult, because it requires a lot of data, a lot of manual work first. Now we have this difference between the two text type when it comes to AI development. Then we have this sustainability problem with funding, or when infrastructure disappears. Well, I could also add to energy costs, because AI uses really big computers, and how can we maintain that? That's the type of thing. Infrastructure is also a big deal. Do you have the necessary networks at your institution to sustain that type of work? Equity and access, who benefit from these tools? Usually institutions with money, that can really maintain a project over certain types. That's why we owe a certain amount of time. That's why we try to privilege also open source. Institutions that maybe don't have as much means in development can also try to use these tools. And then the human expertise is make sure that your data are reusable and can be interpreted later in the future to make them as user-friendly as possible, using standards that we try to all use, like, for example, Darwin Core. You have the FAIR principles. So that's also questions you need to ask yourself. When it comes to the FAIR principles, they are at risk of becoming more and more outdated, and they need to be currently renewed with AI developing so fast, by the month almost, before implementing any project and doing anything. I would really encourage you to ask yourself all of these questions first: infrastructure, metadata, FAIR principles, where do you store your data, what type of standards you want to use. This is the most important questions. And lastly, to remember, technology amplifies humans' capability, doesn't replace them. We use AI as a tool to help us in our work, but not as a final solution.